don't want to bother, sir.
Okay, let's continue with the next section in the same chapter, which is about pulse response. So this is when, yeah, basically the switching phenomena also. We study the response of circuit to a special cause of singularity function. So when step function is when at t equal to 0, you put 1, yeah, input 1 here, like this step. That's why it's called step. Step means one step function. Just like this abrupt change in the input. If it were voltage step, then this kind of signal input signal is implemented using a voltage source plus a switch. So at t less than 0 second, the switch is at this position at 1. So here, when you measure the voltage here, it will be 0 here. At t equals 0, you move the switch to position 2. So the V output here will be equal to this VO. Okay. Similarly, we can do the same thing with current source. So here, in this case, at t less than 0 second, switch is at this position. The current only flows in this loop. When current is at when the time is 0 second, the switch is being moved to this position. Then current starts to flow in this load. Yeah. When it is not 0, for example, when the switching happens at t equals to t0, like this. Yeah. So we express this in the the step function as u t minus t0. So this is basically a step function like this, which is being shifted by t0 second. Okay, so this is the u at t minus t0, a step function which occurs at t0. If t0 equals to 0, then this becomes u t like this, which is similar like this graph. Okay, yeah, I think it's quite easy to understand. Okay, so if we have pulse signal, a pulse signal can be approximated as a combination of several step function. Yeah. At here, for example, if we have a pulse signal which occurs between t equal to 0 until t equals to t, basically this is a combination of ut here plus or minus, yeah, minus times a, yeah, if this the amplitude is a, so aut. Then after t equals to the large t here, t capital, this becomes 0 again. So this is the sum of aut minus minus t capital. Okay, because this function occurs at t equals to t capital, but minus, so here. So this plus this equals to 0. The resultant or the sum will be equal to this pulse signal. Yeah, so we can approximate pulse signals as additions or subtractions of several steps function. Yeah, step function. For example, this one, IT current at t equals to 10 times 10 times 10 times ut minus ut minus 0.01. So the amplitude will be 10, and this is a pulse signal between 0 to 0.01 second. Yeah, this is we draw it like this. Yeah, voltage t now minus 10 ut minus 1 minus ut minus 2. So this is a pulse signal of voltage, yeah, whose amplitude is 10 minus 10 volt, which occurs between 1 second and 2 seconds. Like this. Okay. So sometimes we can have non-zero initial times. The switching occurs not at t equals 0, but at t equals to t0. And we can have repeated switching. So as exemplified by the pulse signal. Pulse signal means that the switching, in this case, the switching occurs at 1 and at 2 seconds, respectively. So in this case, then the general form of the differential equation will be like this. This is still the same as the previous general form of differential equation. Tau dx dt plus x equal to fdh. The initial value at t0 plus, yeah, this is different, not at t equal to 0, but at t equal to t0 equals to x0. The general form of the solution will be xt equals to exponent minus t0 over tau xt0 plus the 1 over tau integral t0 until t exponent minus t minus x over tau, the forcing function times x dx, or be expressed as this becomes k1, the steady state solution, the steady state solution, because at this one, when t equals to infinity, so this value will be very small. Yeah, well, this one is a steady state. Plus k2 exponent, this is the initial value condition. The k2 is obtained from initial value. For constant source, this expression will hold on any interval where the sources are constant. The values of the constant may be different, but must be evaluated for each interval. Okay, let's have a break because it's already recording. Yeah. So again, yeah, the pulse can be approximated as sum of steps. Yeah, sum of steps. So yeah. This, so this is the solution, and this is the common, the general solution. Yeah, this become this is the steady state solution. Yeah, the steady state solution is like this, until from t until t0, from t0 until t, and this is becomes the, so this becomes k1, and this becomes the k2. This one is k2. Yeah. Okay. This expression will hold any interval where the sources are constant. The values of the constant may be different, must be evaluated for each interval. The values at the end of one interval will serve as initial condition for the next interval. So let's say here, for example, you have the circuit. Find the output voltage V output at t larger than 0. This is 100 microfarad, like this. This is the voltage now is not a constant voltage source, but rather it is a step. So basically it is a switching. So there is a switch here where this 9 volt at t equals 0, it is switched on. At t equals 0.3, it is switched off. And like this. So the V out at t less than 0. So this is will be equal to 0. Yeah. So it means this will be also 0. At just after the switching also will be 0. At t larger than 0, this Vt will be equal to 9 volt. Okay. So this is steady. The V output T here will be equals to K1 dash, yeah, one single dash plus K2 dash exponent minus T over tau. Yeah, the tau will be, you put the Thevenin, finding the Thevenin equivalent resistor here from this terminal to this terminal, yeah, which is equals to 6K in parallel with 12K, yeah, or equals to one type, this one. Then the tau will be obtained by multiplying that Thevenin equivalent resistance with the capacitance value, 100 microfarad. We obtain 0.4 second. The V output at infinity, yeah, it means this is steady state. So this is open circuit. equal to the 8 divided by voltage divided, 8 plus 80, 10, yeah, times 9 volt. So this becomes the steady state solution, yeah, the K1. The V output at initial value at 0 plus equals to 0. This is equals to K1 plus K2. So we know here K2 equals to 0 minus K1 or minus K1 dash. So V output will be equals to K1 is the steady state value. Here is, yeah, this one, yeah, 9, 8 divided by 18 times 9. So 4. This is 4 volt. K1 is 4. K2 is 0 minus 4, minus 4. So this is minus 4. Okay. The tau is 0.4 second. So this is valid between 0 to 0.3. So at t larger than 0.3, the switch is turned off again. So Vt equals to, this Vt equals to 0. So T0 becomes 0.3 second. So we have to find then the V output, the initial value at 0.3 second. We calculate using this equation. So we insert the t equals to 0.3. Okay. So we obtain the value here. Then V output t will be K1 double dash plus K2 double dash exponent minus t. Now the T0 is not 0, but instead it is 0.3 second divided by tau. The tau is still the same because no changes in the capacitance. So it's 0.4 second. The V at infinity will be equals to 0 because it is steady state now. This is a short circuit. The Vt is 0. It is steady state, so this is open circuit. So then the V output across here will be 0 volt. So K1 double dash is 0. So from here we obtain K2 double dash equals to this initial value minus 0. Yeah. The V output. Yes, hello. Can everyone hear me?
Yes, sir.
Yes, sir.
So I think the connection got disconnected for a while. Sorry, yeah, for the interruption. Okay, so from here, then yeah, itu dash. So the output at after t equals to 0.3 will be like this. So it will be a decaying function. Yeah. 2.11 exponent minus 3 minus t minus 0.3 divided by 0.4. So if you draw it from between 0 to 0.3, the equation will be this one. Yeah, at t equals to 0, this equals to 1. So this equals to 0. At t equals to 0.3, the value is 2.11. This is the initial value. But then at t equals to 0.3, then it decays. So the solution will be this equation. Yeah, decays like this until it reaches 0 at infinity. So this is another example when we have the switch is initially at A. At time t equals to 0, it moves to B. Then at t equals to 0.5, it moves back to A. So this is a pulse, but an inverse pulse. So at between 0 to 0.5, it is 0. It is called as piecewise constant source. Before it was 12 volt. After 0.5, it is 12 volt. On each interval where the source is constant, the output is in this form. Yeah. And the constant are determined in the usual manner as before. For t larger than 0 until 0.5, the switch is at B. The solution is like this. Yeah, the V output at plus here just at 0 second, just after the switching happens, is 12 volt, the initial value, which is equal to K1 dash plus K2 dash. V output at infinity equals to 0. equals to K1 dash. So tau is obtained. So we obtain the solution to be 12 times x1 minus t over 0.2, and between 0 to 0.5 second. For t larger than 0.5, switching at A, it becomes like this, yeah, the solution. So then this is the V out, the initial value at 0.5. It is just be that the value at just after switching equals to the value just before switching, the output. So from here, then we obtain this value, this solution, okay, for t larger than 0.5. So if we draw, it looks like this. So it initially it was 12 volt, yeah, before the switching. After switching, it decays, reaching this value at 0.5, calculated to be 0.985 volt. After that, it increased again until reaching 12 volt. Okay, so that will be all for